So welcome to the lecture course on quantum gravity. So today I finish chapter 3 and I will also start with chapter 4. So recall chapter 3 is not directly on gravity, it's on so-called reparametrization invariant systems. But the tools that we learn there are very useful then when we deal with quantization of gravity. And the advantage is that the formalism is still simpler here, so it's good to learn it here and to apply it then in a more complicated situation later. Now, this last part, 3.3, is on parametrized field theory. Now, so far, we only had mechanical models and we had a string. So just to repeat, we had in section 3.1, we had first the parametrized non-relativistic particle. And just to give you the essentials, and this is of course a well-known system. Yeah, we have an action in mechanics, say for one particle in one dimension, and the standard way would be to write this as an integral over a Lagrange function q and dq over dt from t1 to t2. And we could parameterize this in a somewhat artificial way by elevating t to the level of a dynamical variable. So instead of just q, we have now q and t as dynamical variables, and both depend on an arbitrary parameter tau. So we have a q of tau and a t of tau. So we had this action S of a q of tau and t of tau, which we call an integral over the tau of a different Lagrange function L tilde of q dot and t dot. Now the dot is a derivative with respect to tau, and you see this new Lagrangian has then also a velocity t dot in it. And then we made the formalism, and in particular we have to note that there is a momentum conjugate to t, because you have a dl tilde over dt dot. So we had this pt is dl tilde over d dot, and turned out to be minus h, and h is the Hamiltonian that belongs to L, the original one. So which means that t and h or minus h are canonically conjugate. Not too surprising if you view in view of the energy-time uncertainty relation. And we defined, so this is a constraint, so we defined a function hs by pt plus h, and this is to be 0. We use this Dirac weak inequality sign, which means it vanishes as a constraint. So that's what you get, and this is a result of the parametrization invariance. I showed you all of this last time, because you get the result that if this is time reparametrization invariant, then you have constraints, and this is also the case for homogeneous systems. This is a homogeneous system, so that if you multiply the velocities by a number, the number just goes out. And then you can have a new action S, which is integral over d tau pq q dot plus pt t dot minus the n times hs. So in addition to the usual one, you have this, but now we have to consider that we have a constraint, that pt plus h is equal 0, and we add this with a Lagrange multiplier, and we call the n the lapse function, and I gave you the interpretation. It's just a lapse of Newtonian time with respect to parameter time. Now the relativistic particle, this was our next example. Relativistic particle is already parameterized. Now the action is the length along the world line, so we treat a massive particle, m unequals 0. And usually we take the proper time, the eigenside proper time, but we can use some reparameterization of it. And again, we have a constraint, so this is already parameterized. And the constraint is something you probably know, or p squared plus m squared as a constraint is 0, which is the mass shell condition. This is p mu, or eta mu nu, p nu. And you can have also then the action in analogy to here. S is integral d tau from, you have p mu x mu dot, I mean this is p mu minus, and then you have n times hs. Okay, if I call here also this hs, I mean it's different from hs from here, but it's the constraint. And this has the interpretation of lapse of proper time with respect to the parameter. Then the next example was the string, the bosonic string. This was in section 3.2, bosonic string, which in a sense is the simplest example of a field theory, where in addition to just the time dependence, you have some space dependence. And the string has a two-dimensional world sheet, so it's one-dimensional at a certain time, and it propagates here in an embedding space, so space-time, so you have here this parameter sigma and tau. And again, I don't repeat it, I did it last time, and again you go through the formalism. Now you have a reparametrization invariance on that world sheet. This is something geometric, so you can use coordinates tau and sigma, but you can use tau prime, sigma prime, whatever. As in relativity, if you have some geometry, now you can use whatever coordinates on it. And because of that, again, you have constraints, but they are now local constraints, because in addition to the time at the beginning, you have, say, the sigma dependence, and so you have local constraints of the form. So we wrote them as H orthogonal. Well, in the quantum version, it was given on x mu of sigma equals 0, and there was not one other, H1 on psi on H mu of sigma is equal to 0. So I should say here, when you quantize that, so I presented this quantization scheme of Dirac, where you apply the quantum version of this on physically allowed wave functions. Here you get just a Schrödinger equation. And here you get a Klein-Gordon equation. No, and here you get new equations, of course, because this is a string, is not something that we do in elementary courses. And we get this here. And I only said a few words on the relation to the standard string formalism. It's in the book, but I did not cover it last time because the course will not focus on string theory, so it would be not necessary. But you can actually translate these equations to equations with these else and so on that you usually have, and you can discuss the Virasoro algebra and all that. Okay, now that's so far a brief review, and just to put today's topic into context. Now we go one step further, so in increasing complexity after the string. Now we go to field theory, say field theory in 4 dimensions, could also be higher dimensions. I do not restrict. And I restrict myself to a scalar field. So we have now field theory. And we have a scalar field, phi, that lives in Minkowski space-time, and the coordinates in Minkowski space-time I call here capital X mu. You will see why, because when parameterizing them I need the small letters. So this consists of the 0 component, which I call also t, and the other components, and a is 1, 2, 3 in 4 dimensions, but you could add here more. I mean, all of what comes is independent of the space-time dimension. And now I can write down the action. I will later do it. But what I want to do here is to proceed similar to here, to parameterize the capital X mu. Now here I introduce the tau and parameterize t. I have a t of tau. And here I do now the same with the 4 of them, the t and the xa. So I make a parameterization. And so I have x mu and these are called the small x mu. And it's the same as x mu of t and xa. So the t is the x0. And these are x1, x2, x3. So I let these Minkowski coordinates then depend on arbitrary space-time parameters. I mean, the picture would be such to have here, say, I draw it for 2 dimensions because it's a blackboard. So t, and there are the other x's, say x1, it's called xa, and then you have here hypersurfaces, but they can be arbitrarily curved. I demand that they be space-like, but otherwise they are arbitrary. And so here this is say t, and this is say t plus dt, and I have here say a coordinate xa. And here I have xa, say, plus delta xa. So, but I can choose freely coordinates here on this hypersurface. So parameterization means I have here, I mean, this, for example, is x mu of t and xa with t fixed. Then I have other t's. So this capital X mu then is assumed to become dynamical as before. Here this time t became dynamical and describes a 1-parameter family of space-like hypersurface. And dynamics means they are not frozen to, as we usually have, so flat 3-dimensional slices. They can be arbitrarily curved as long as they're space-like. So this becomes dynamical and describes a 1-parameter family of space-like hypersurfaces. So in principle I could now go on with the similar formalism to here, but I think you need not much fantasy to recognize that, of course, formally this is a bit more difficult. So I will not do it in all the details. In principle, if you have understood what we did here, you will be able to do it here. So I leave the details as exercise, or you can read it up in the book if you like. You don't. But I think you can try it as an exercise. But the important steps are the following. So I start with the original action, which is the analog to this here. So the original action is the standard action in Minkowski space. So I write here, now I restrict to 4 dimensions. And you have some Lagrange density depending on the field, and I assume its first derivatives. course, you can write it out, a kinetic term and some potential term, but I leave it general. I do then the parametrization. So you see here, I introduce this d tau instead of dt. So I wrote, dt is dt over d tau, and the dt over d tau was the t dot, and something similar is done here. So I write this as the integral d for x, and then of course it's the Jacobi determinant that enters here instead of just the derivative, and you have L of phi, and this here I rewrite as d phi over d small x nu times d small x nu over d capital X mu, and I call this again as before integral d for x and L tilde. So this is of course the standard one, so it gives the Jacobian for the variables capital X with respect to the small x's. So I write it as the determinant in this way. I think you know what it means, and this just corresponds to the t dot above. Just that you go from a particle, to 4 dimensions in field theory. Okay, so the formalism proceeds as in above, so you can have this as an exercise, or you can just read it up in the book. You can define the momenta, you have to calculate the Hamiltonian and all that. And you find the following, you find again constraints, because now we have, with respect to these parameters here, we have reparameterization invariant. So if you have this slicing, you can of course use another slicing by using other parameters, but you have the same physical situation, the same Minkowski space, and you get constraint, and these are now 4 constraints, the so-called H nu. Now this is 0, 1, 2, 3 if I restrict to 4 dimensions, and this is then defined, this is the analog to this here, which is here just the pt plus h, so you also expect here a linear term in the momenta, in the field momenta, and something that has to do with a Hamiltonian. And what comes out is pi mu, so that's in fact then the dl tilde over the dx dot. Here, so I don't write a tilde here. And then we have here a term, so this Jacobian enters, and we have dx0 over dx mu. And you have here the energy momentum tensor. Now here we only had the Hamiltonian because it's mechanics, but if you go to special relativistic invariant field theory, of course the energy momentum tensor replaces the Hamiltonian because it's covariant. You not only have the energy density T00, but also the corresponding momenta and energy fluxes. And so it's no surprising that this appears. So this is the energy momentum tensor. And this energy momentum tensor that is derived from L, from the original L. So by your standard formula, which is a generalization of the formula for the Hamiltonian. Hamiltonian in mechanics is pq dot minus L, and a corresponding formula you have for T mu nu, which you recover from L. Yeah, and this is a constraint, so it's 0 as a constraint. So that's the new thing, and as I said, it's formally a bit more effort to do all that and keep track of derivatives and of coordinate transformation, but nothing new is in principle added to this, what we did here, just that it's more complicated. So this corresponds to the HS is PT plus H. So that's the new, this is momenta to these now dynamical x's. Here it was the momentum conjugate to the now dynamical t, and here we just had a Hamiltonian, and here we have this more complex thing, but basically it's the energy momentum tensor. So you can then write the action in the following way: integral d for x. So p phi tilde phi dot minus h tilde. Okay, so this is dl tilde over d phi dot. I just have here tilde because it comes from here, from the tilde. And also this here comes from the tilde. It's not a constraint. This is if you just calculate the Hamiltonian density by the usual Lagrange transformation here from L tilde. And this can be written as integral d for x p phi tilde phi dot plus pi nu x nu dot minus, and then we have again Lagrange multipliers, but now we have 4 of them because we have 4 local constraints. I call them n mu, h mu. So you see, instead of this version, like here, no? So instead of this old version, well, it's not written here, but last time I had it pq dot minus h. I have here this new version where I have, in addition, now this elevated parameters from Minkowski space or coordinates, but I have then constraints. I mean, that's the price I have to pay for having this freedom of parametrization. And I add them with Lagrange multiplier. So the sum goes over from 0 to 3. So to accommodate h nu equals 0, I add them with 4 Lagrange multipliers. So this I should maybe that it's clear. It corresponds to d tau pq q dot plus pt p dot minus n hs. Now, so in mechanics you have just one simple Hamiltonian, one lapse, and here you have these densities, 4 of them and 4. It's now convenient and also favorable if we decompose these constraint into components, into one component normal to a hypersurface and 3 components that are in the hypersurfaces. And you will see then, maybe already today, but also next week, when we do the canonical formalism for general relativity, that we do there the same. Yeah, it's not Minkowski space, but we start with a curved space-time that is a solution of Einstein equations, and we take any foliation, any curved or whatever foliation, and then we make a formalism that is called 3 plus 1 because we replace the 4-dimensional formalism by 3 dimensions plus 1, and we need this for defining a Hamiltonian and the Hamiltonian formalism. So it's not like what I did before, the covariant formalism, the path integral, but it's the canonical formalism where you identify p's and q's and a Hamiltonian. And it is for this reason that we have to develop this formalism. So we have here the hypersurface, and then we have, say, a normal vector. Everything is local, but maybe if you're on this point, you have a normal vector with components a mu, and then you have here tangential components, which I call x mu comma a. So this is the partial derivative with respect to the 3 spatial directions, and because they are spatial derivatives, they lie in space. They are tangential. So here, so that's here orthogonal, and so we have here, we then define an H orthogonal and so-called HI, in that we here contract this with the normal vector and this here with the tangential vectors. So this is 1 constraint and these are 3, and they are local constraints. I say this many times because it's so important, because this is they depend on the space point. It's not like mechanics where you just have one particle. It's field theory, so it depends on the space point. And they are constraints, and because this is a constraint, I mean, there are also constraints. And this is then, if you then quantize, or if you would we do it later, but from there, then you would get similar things to the bosonic string. I mean, the bosonic string, in some sense, is a 1 + 1 dimensional field theory. And this is why here you have 2 local constraints, but here you have 4. Yeah, and then we have the action S, which is an integral d for a small x, p phi tilde phi dot, plus the capital pi nu x nu dot. And then instead of here, this 4-dimensional sum, we replace this by n times h orthogonal plus na times ha. So this is minus n times h orthogonal minus na times ha. Okay, now we have these Lagrange multipliers n and na. So what is their interpretation? Of course, we assume that the n still has something to do with the lapse. Now you have in addition this na, and the interpretation you get from Hamilton's equation of motion. Now, if you have the Hamiltonian, you have Hamiltonian's equation of motion, for example, as q dot is dh over dp. And if now I write this in quotes because we have no mechanics here, but you know that equation. The second one is p dot is minus dh over dq. And if I apply here this one to this action with this Hamiltonian, then I get x dot nu is d, so that's then the Hamiltonian, and h orthogonal plus na ha over d pi nu. And okay, from this explicit expression, you see that this is n times n nu plus na x nu, x nu, comma a. That's the x nu dot, and it's also often called in the literature T nu. This is a timeline vector that goes in the direction of the coordinates x1, x2, x3 from one hypersurface to the other. And maybe it's appropriate now to draw a picture so that you have some maybe geometric feeling for that. So we have here, say, one hypersurface, and we assume that we have one infinitesimally neighbored. So that's one hypersurface at, say, t equals constant, and this is another one at t plus dt. Yeah, so you have here coordinates, spatial coordinates xa, and you can choose them freely. No? That's what parametrization means. I mean, they are arbitrary, so perhaps here they are there. And, okay, infinitesimal labeled would be maybe here. I mean, it's just a picture, but we need that later, dxa. And so we need a vector that points here from here with the coordinates xa to here to the neighboring one with the same coordinates. And that's our, we call it T mu. This is our T mu, that is here, T mu. And because everything is infinitesimal, otherwise I could not draw vectors, right? Because everything is curved here on at least on the surface. X mu T mu dt, which is the same as dx mu, or the same as x mu dot dt. Now I can go to that point either directly or through another way, in that I first go on the first hypersurface to a point that is directly in a perpendicular way below the XA on the second. No? So I can here draw a perpendicular line, and I go then here, first here, so that's perpendicular, so that's here the proportional to the normal vector. So I have here then n times n mu dt, and this here is n a x mu comma a dt. No? So I first go, so I have here a point with coordinates xa, and I can choose any point here giving the same coordinates xa in the next. Yeah? So that's my freedom, and this freedom I can encode in this n and na, and instead of going from here to here, I can go first here and in the tangential, yeah, and then go along the normal. And we call n still the lapse function. No, that's not appropriate. N, the lapse function, like for the particle. No, so before, recall here, we had, n was dt over d tau, and here it also has to do with going from t to t plus dt, but because these are whole hypersurfaces, you can do this at any point. Yeah, so often people call it a many-fingered time. Well, it's infinitely many fingers, because at each point on the initial hypersurface you can erect a normal, and you get a final. And actually the choice of this other hypersurface is determined by the choice of this function n. Yeah, so you're free to have to start from this and then erect at any point. You choose your n and then you get the next. And you can already see that this somehow encodes the general covariance that we will then have in general relativity. Although here space-time is flat. And NA, this is the new, well, we had it in string theory, but I did not discuss it much. So these are the components of the so-called shift vector. Components of shift vector. Now, shift means is obvious geometry because you first shift this here before you then go in time upwards. So you have 3 shifts and 1 lapse in a 4-dimensional theory. If you had a 2 plus 1 dimensional theory, then you had 2 shifts and 1 lapse, and so on and so forth. Yeah, I should say that I think this formalism with lapse and shift goes back to Arnovitt, Deser, and Miesner. So these are 3 US-American physicists, Deser and Miesner. Miesner is also co-author of that famous thick textbook on relativity, gravitation, Miesner, Son, and Wheeler. Because of that, you find there also a nice chapter written by Miesner on this lapse and shift and all that. You can also read it then in that book, because this was already done end of the 50s. In a couple of papers, there is a review of 62, but there were 5 or 6 original papers before that. Yeah, so both Deser and Miesner, I think, died last year. And this is why it's often called, this formalism, also the ADM formalism. So when you read about canonical formalism, ADM formalism, usually people mean the same. It's just if you want to emphasize that this goes back to ADM. I mean, not these parametrization things, this were done earlier, but this particular decomposition. Now, we can start with decomposing 4-dimensional quantities, and next time I will do everything also for the Einstein-Hilbert action and for these curvatures. But now we start with the metric, and we are still in this example of well, I should say, I mean, I have here assumed the Minkowski space background, but you can use the same formalism for curved background. Yeah, so I did not yet talk about Einstein equations, but you can have a curved space-time, four-dimensional space-time with metric g mu nu of x here, and you can decompose it in this way. I mean, if you want, I mean, this ds squared, you can go from x to t plus dt, but also to x plus dx, no? Because these are the infinitesimals, and you can decompose it in terms of lapse and shift. And from the diagram, you can see that this is minus n squared dt squared. So instead of going here, you first go this, and because the normal vector is n mu is -1, you get a minus sign for the time. And then we get a three-dimensional part, and there a new quantity that will accompany us for many hours occurs. This is the three-dimensional metric, H, which I denote by HAB. Many people denote it by HAB, some people give another expression. Gamma is also sometimes used, but I call it HAB, so that's the three metric. It's a metric that applies to the three-dimensional spaces. Three metric, and you have dxa plus na dt times dxb plus nb dt. Actually, the three metric is what we call in geometry the induced metric. So this is the induced metric. So this is the metric that you get from the space-time metric by projecting to this three-dimensional hypersurface. So if you have this formula HAB, going back to Gauss, g mu nu dx mu over dxa dx nu over dxb. So this hypersurface are given by capital X mu, dependence on for fixed time, x1, x2, x3, and this gives you then the induced metric HAB, and yeah, so you can check actually that this HAB, NA dt, NB dt terms, if you insert that, gives just, I mean, this vector with the x mu comma I. So instead of going directly, you go here and you go here. So you have this ds squared as HAB NA NB minus n squared dt squared plus 2 HAB NA dxb dt. And then you have the three-dimensional part, maybe to indicate that, I can give you a different color, plus HAB dxa dxb. So they have decomposed the four-dimensional line element into the purely spatial one and the ones that have to do with time and involve lapse and shift. So massless scalar field in 1 plus 1 dimensional Minkowski space. And so the standard Lagrangian should be familiar to all of you. Lagrangian density, which is a function of phi, d phi over dt and d phi over dx. Only first derivatives occur here, and because two dimensions, x0 is the t and the x1, which is the only space one, is just x. And then the standard action is -1/2 eta mu nu d phi over dx mu d phi over dx nu. And you can also perform the sum. These are only two components, so this is 1/2 d phi over dt squared minus d phi over dx squared. So if we talk about the x mu of the small one, we only have two, no? Here the capital T and the capital X, and also here only two, no? The x0 and the x1. So we have T of x0 and x1, and we have x of x0 and 1. And yeah, not surprisingly, we denote derivatives with respect to x0 by a dot and derivatives with respect to x1 by a prime. Yeah, so dot is derivative with respect to x0 and prime is that. Yeah, and then you can do the formalism here. It's I think it's a nice exercise. So and derive these constraints, the Hamiltonian and the constraints. Maybe I already said last time, but I should again hit this time. So this, if although in strings here, the first is called Hamiltonian constraint, and the other one is called momentum or diffeomorphism constraint. But we will do this in relativity and define it there generally. So the H orthogonal, you find the following: 1 over square root of x prime squared minus t prime squared, and then you get x prime pt plus t prime p by x plus 1/2 p phi tilde squared plus phi prime squared. So that's often called the kinematical part, and this is often called the dynamical part. The kinematical part because it has to do with the embeddings, how you embed the things into space-time. But the original dynamics is in the scalar field. And yeah, so you might be worried that this square root can become 0, but if you restrict to space-like hypersurfaces, the discriminant is always positive. You can, because the corresponding vector is space-like. So you cannot have problems with that. And then you have one second constraint. I mean, here, of course, you have 1 plus 3. Here you have 1 plus 1. And this is t prime pt plus x prime px plus phi prime p phi tilde. So these are the constraints here that you should find by just taking these results and applying it to that, to a concrete Lagrangian, not just general, but a concrete simple Lagrangian. You could also do it for other Lagrangians if you like. Yeah, now that is parametrized field theory, so this is why here these things are linear only in the momenta, not quadratic as you would expect for genuine dynamical momenta. The kinetic energy p squared over 2m. Whenever you have something, also in field theory, you have squared momenta, but here you have linear, and this is looks like this one, right? It shows by itself that you can deparameterize it. Although later in relativity we will see that these things are quadratic and you cannot deparameterize. You have to live with this formalism. The formal quantization then occurs if we impose commutation relations. So the formal quantization means then for the general case and not just for 2 dimensions, I mean you have x mu of x and pi mu of y is I h bar delta mu nu delta of x, a 3-dimensional delta function, and phi of x, p phi, well actually a tilde, but never mind, is I h bar delta of x minus y, and the others vanish. No? The x's among themselves and so on, they vanish. I don't write them down. No? And then you can replace this pi by h bar over I times the functional derivative with respect to x. And you can apply this on wave functionals, which are here, well, in our example, here with two dimensions would be psi of phi of x, t of x, x of x. So that would be then the wave functional. So like in the string theory, you have then here in this example, which is just 1 plus 1 dimensional phi of x, t of x, and x of x. And then you can explicitly substitute here. Well, do I do that? Yes. These, yeah, I do that with the derivatives, with the momenta by the derivatives. Substitute then, I mean, pi nu by h bar over I d over dx nu, etc. Now you know this from quantum mechanics, where in the position representation we replace p by h bar over I times t over dq or nabla. Well, this is a formal recipe. I mean, quantization is not a derivation that leads to a unique result. No? So quantization always means that you guess a quantum theory from the classical limit. And you have all the ambiguities with factor orderings and all that in variables. So that's what we mean here with quantization. And you then get, as for the bosonic string, then this equation H orthogonal on psi is 0 and H. Now we are still in the this is the general recipe, but I show it explicitly for the example. Psi is 0, and if you write this explicitly, yeah, you just take these expressions and you replace all the momenta by these derivatives. And so this, there you get 1 over square root of x prime squared minus t prime squared, and you have minus I h bar x prime of x d over dt of x minus h I h bar t prime of x d over dx of x. So this is from the kinematic part here, and then comes from this dynamical part plus 1/2 minus h bar squared. And then you have second derivatives. Plus phi prime squared of x. Yeah, I think I have all the. I hope this is clear. Of course, there are many nasty things hidden here when you write that with the functional derivatives, and some of them you will encounter that because these are functional derivatives and things are at a space point, that often you find divergences, as you always find in quantum field theory. But at least formally we can write this down, and formally we can handle it. So you have here these two terms with first derivatives. So like in the Schrödinger equation, no? This, when you quantize pt plus h equals 0, but then you have this part that comes in the quantum mechanical in the mechanical example from the h, here this dynamical part, and this here also, if you have here explicitly, so we have here h bar over I t prime of x d over dt of x dt of x plus x prime of x d over dx of x. I hope it's always clearly visible here. That's my writing here. X plus phi prime of x d over d phi of x 0. Yeah, so that's these are the two equations, and we will encounter when we do relativity also equations that are constraint equations, but where here all these terms are quadratic in a sense. So which means that in relativity you cannot say this is just an embedding, but all of these things are equally dynamical. That's the difference from that between Einstein's theory and say just an artificial parameterization. I mean this here. So that's like, maybe I write it down again, is called Hamiltonian constraint. And this is called momentum or diffeomorphism constraint. And this has a simple meaning. Well, first I also have done something to simplify things. So already here, I mean, of course I could also have written the momenta to the left-hand side. I mean, these are classically, these are just numbers. But if I had it with the left-hand side, then I would have this functional derivative to the left-hand side also. And this would also first hit this here. So you would get something different. No? So choosing this and replacing it at the right-hand side already introduces a factor ordering, if you like, a particular commitment to the quantum theory. And certainly this is the simplest if they just act to the right. But no one can force you to take another one. This here has a simple interpretation, and this has to do with the name diffeomorphism constraint, because this equation, and this holds for all the momentum constraints that you will encounter, this equation guarantees that the wave functional does not change if you change the coordinates on the three-dimensional space. So this here, I mean, I can show you this for this example. So if you make a coordinate transformation here, x to x bar is x plus a function, I call it delta n1, because it's in space, so it has to do with the shift. And then the t of x goes to t of x plus delta n1 of x, which if I expand a la Taylor is t of x plus t prime of x delta n1 of x. Also I neglect the higher dimension, higher order terms. The same holds for the x and for the phi. It's just the very same. And so the psi, the wave functional, then transforms to psi of t of x plus t prime of x delta n1 of x, and also the others just the same. And if you expand this a la Taylor, you have here psi of t of x and so on, and then you have the integral dx, and you have t prime of x d psi over dt of x and so on, delta n1 of x. I just put the delta n1 here and the t prime here for illustration. Yeah, and then you see here this from you have here also the other parts, no? And this just adds to, now I should say here, t prime delta over dt, and the others, they follow, I mean, step by step. I just did not write them out. So by that constraint, this is just 0. And so this means that if you change the coordinates here, the wave function does not change, which makes sense, because otherwise, if this is a coordinate dependent object, you would not be sure, I mean, how to treat it. And this is always the interpretation of the momentum constraints. Also in relativity, you will see that we have Hamiltonian and momentum constraints, and the momentum constraints just have this interpretation that on the three-dimensional slices you can change arbitrarily your coordinates. In fact, for relativity it was Peter Higgs who later came up with the Higgs particle, but before worked on relativity, who showed that. More or less a calculation analogously to that here. But we will come to that when we do relativity. Now we come towards the end of this chapter 3, but there's one important thing that, of course, must not be dismissed here, because it will be of central importance then later, and these are the commutation relations, or first classically the Poisson bracket relations between the constraints. Yeah. So we had above that the full Hamiltonian is the sum of the constraints NH orthogonal plus NaHA. Now we had this in the action, we had this as the Hamiltonian, the super Hamiltonian, and because it's a constraint, we do a la Dirac, it's the Hamiltonian constraint. And the constraints, okay, these are here, of course, should be preserved in time because they should be valid everywhere. These are general constraints with respect to parameter time x0, which means, that the Poisson bracket of this with the constraint should vanish. And this means that, the Poisson brackets of these things among themselves should be a combination of themselves, no? Because then when you go to the constraint surface where they vanish, then it vanishes. No? So constraints must be preserved, and these are the constraints. There 0, 0 must be preserved with respect to x0. And this means that the Poisson brackets between the H and HA must be a combination of themselves, because otherwise you would not have this preservation. Okay, now that means one has to calculate explicitly, now not just in the example, the Poisson brackets between them for the parametrized theory. Now that's not an easy task. You can find it in the literature. It's one of these many things that occur in theoretical physics that are straightforward but very lengthy. So it's clear what to do, but you must spend some pages to find the result. No? So what we do? So and you find this first calculated in a paper by Dirac of 1951, who discussed these parametrized theories, and also later he was one of the pioneers of the Hamiltonian formalism for general relativity. Now Dirac, I give just the result. So these are the Poisson brackets between H orthogonal of X and H orthogonal Y, because it depends on space, so it's also among themselves. Then about HA of X and H orthogonal of Y, and then between the HA of themselves. This is then the so-called constraint algebra. Okay, so what is the result of this when you calculate? So for the first, there is one parameter I will explain in a minute. It's important, so I will give it a red color, sigma. And then there are delta this delta comma a means a derivative of a delta function in the direction xa of x and y. And then we have HAB of x, HB of x plus HAB of y. HB. So, and here this is simpler. It's just H orthogonal delta comma A x comma y, and this is HB of x delta comma A x and y plus HA of delta. And the derivatives are all with respect to x, not with respect to y. Okay, this is what you get after a somewhat lengthy calculation that Dirac has done for us long ago. And now, what is the sigma first? The sigma corresponds to the signature of the space-time metric. So if you have a space-time metric with signature, so I write it in that way. Where is that color? Usually we have minus 1, 1, 1, 1, but I can also write here sigma 1, 1, 1. No? So why that? Because we know that it should be minus 1. Yes, in general relativity it's minus 1, but sometimes it's useful and people like that to do so-called Euclidean formalism of quantum field theory, and so have a space-time that is not a space-time but a four-dimensional space. It has many calculational advantages to do that. And so you see here explicitly that the signature of space-time enters here in the first relation. So that time in particular is different from space. You recognize from here by this sigma. Some people also discuss a degenerate case, sigma equals 0. Maybe I say some words later. Sigma equals 0 is something which you maybe find just stupid to think about. This is a so-called Carroll limit, Carroll group, because there you have no motion at all, because then you have speed of light goes to 0. In that, okay, speed of light goes to infinity, you get the Galilean limit. And speed of light to 0 means that the light cones don't go this way, but just go to the axis, and there's no movement possible. That means every one is frozen at this particular point. This Carroll refers to Lewis Carroll, who wrote Alice in Wonderlands. Was a mathematician. Yeah, okay. That will occur later. Now the other thing for the first is that here on the right hand side you have explicitly the 3 metric. So this means that it is not a so-called Lie algebra. Many of you have heard, I guess, in their lives about Lie algebras and Lie groups, and so these are commutation relations where you have some generator, say GA, GB, and closes on GC, but without having the dynamical variables occurring, just structure constants, epsilons or whatever on the right hand side. So, but here you have explicit functions here, and this is why it is an algebra, but not a Lie algebra. So this is algebra, but not a Lie algebra. It has, instead of so-called structure coefficients, has structure functions. So it's something more general. There is, of course, an exception. The exception is in 2 space-time dimension, and this is part of the reason why string theory is also special, because there this does not occur explicitly. So exception, except in 2 dimensions. That's to do with the conformal symmetry that you there have. This is a subalgebra. This is just among the momentum constraints on the 3-dimensional surface, and you see this closes perfectly. So this is a subalgebra. It's a Lie algebra. And this shows you that the non-trivial things have to do with time as often, and with the 0, 0 component, and with going away from a hypersurface. On the hypersurface, even if you have 25 space dimensions, it's nothing special happens. Yeah. Okay. If you calculate this for the bosonic string of last time, which I did not do, you find the same result. Except then, of course, that this is not explicitly there. So because you have some combination here with the square root of the determinant and then the HAB, which in 2 dimensions cancels. So why is this the same for the bosonic string? I mean, here this is nothing with strings. This is just parametrized field theory. Now the point is that this algebra has a purely kinematic interpretation. So it's a so-called algebra of hypersurface deformation. So if you're just mathematicians, I assume you do not know anything of relativity or physics, but you know much about mathematics. Then you can discuss the problem that you have a curved space and you foliate it into hypersurface, and you then calculate the algebra of the deformations, which means you have a normal generator, that in our formalism would be with this n, and you have tangential coordinate transformation. And if you just calculate this mathematically, you arrive at an algebra for these normal and tangential deformations, which is just that algebra. So the algebra has a pure kinematic interpretation. That's the algebra of hypersurface deformations. And from this it's also clear why, maybe it's erased here, that the invariance, the invariance is not the one of full diffeomorphism invariant, but the one that I wrote down earlier, that x0 goes to x0 plus a function of the spatial variables only. Because if this is the algebra of hypersurface deformation, of course maybe you have one hypersurface in the projection, so, and another one maybe that cuts here this one, and then of course you can, so this is maybe sigma 1 and sigma 2, and then of course you can make, say, here a deformation with respect to this, to sigma 1, a normal one, and you can make another deformation with respect to sigma 2 at the same point. So you have no unique transformation at a point, but this is not the case for diffeomorphism. There, I mean, if you have a point, then you have a unique, say, coordinate transformation or diffeomorphism. So you can do in principle more here with that. Okay, this we will see that plays a role later also. Yeah, now I mentioned string theory. Of course, classically, you can formulate it in this way, but you can also formulate it with these functions L, Lm, and L0 that I think the string theorists usually prefer. And the quantization then of this is, in quantum gravity should make all of this into operators. And the question is, of course, what happens if you have then here, instead of Poisson brackets, commutators. And of course, you would expect that also they should be preserved. That also then on the right-hand side you have the operators. But those of you who know a bit of strings, you know that this is not the case. We know that there's something else, a so-called central term. That's called the Virasoro algebra. Now, whether it's what happens in general relativity is unfortunately largely an open issue, and one of the things that we have to discuss then when we come to relativity. So this finishes chapter 3, and chapter 4, which we do next week in one session, before we come to chapter 4, will be devoted to the classical canonical formalism of relativity, and chapter 5 will then be the quantum version of that. And for 5, this is maybe a central part, like chapter 2 was for the covariant formalism. So there we will have more. They will devote 2 sessions, for 5. But we have to do these preparations. So next week, to have the classical version of canonical formalism of Einstein's theory, the ADM formalism, if you like. And with that preparation, I think you should be able to easily follow, because we shall do this 3+1 decomposition for the Einstein-Hilbert action. So the Einstein-Hilbert action is an integral over d4x, and you have the Ricci scalar, very nice and short, but you can also split this up into the dynamics of 3-dimensional hypersurfaces, just for the purpose of defining a Hamiltonian and a quantum evolution. And this we will do. So we will identify what is the Q, what is the P, what are the constraints, and how we interpret the constraint. This is already interesting from the classical point of view. Even if you're not interested in quantization, it gives you a totally new aspect of general relativity. I should mention, one path to this geometrodynamic version, as it's also called canonical and geometrodynamic version, is the so-called 7th root to geometrodynamics. Now, what is the 7th root? I already mentioned the thick book of Misnerson and Wheeler, and there is a box. There are many boxes this box presents 6 roots to general relativity. 6 roots. So Einstein's original derivation, then Feynman's derivation that we only have briefly encountered with the spin 2 degrees of freedom, then of course the approach with the action and so on. And in the 1970s, 1976, Kuchasch, Hochmann and Teitelbaum have added a 7th root to that. Now this paper is a most interesting paper, about 40 pages or so. In my book I have summarized it, but unfortunately time is lacking to present the 7th root here, so we will do only the standard derivation. But I can tell you what the 7th root is. The 7th root is the following. So Kuchasch, Hochmann, Teitelbaum, they start from this algebra. And then from algebra of hypersurface deformations. And then they want to implement this by deriving explicit expressions for these H's. And there's of course an assumption. You always need an assumption. The assumption is that only the metric enters from the geometry side. And of course, when you have a canonical formalism, it's the 3 metric, and you will see its canonical momentum, but no Brans-Digge type fields or whatever. And they can then derive from this algebra and from a principle that says it does not matter along which intermediate hypersurface you come from the first to the last, so you can do whatever you want in between. So it's called path independence. You can then derive explicit expressions for this. And surprisingly, this is also what comes out when we do the 3+1 decomposition of general relativity. So you could, even if you were totally ignorant but excellent in mathematics, ignorant in relativity but excellent in mathematics, you could then derive from this the canonical formalism of relativity, and could also then derive the covariant formalism that is just Einstein's theory. So you could actually derive Einstein's theory from the algebra of hypersurface deformation. So that's something I would have, when I first read this, totally unexpected, but very instructive. So I do not, it is very nice, but it takes then 2 hours alone to derive that. But you can read about in the book summary, or you can read these 40 pages in the original article. And what they find is, okay, you can fix the theory, the action up to two variables, and these are can be identified with the gravitational constant and the cosmological constant. So there are two parameter freedom you have, and with a certain physical dimension. And if you demand then that the result is equivalent to Einstein equation, you see, aha, this can be identified with G and lambda. So you see how, in a sense, how rigid Einstein's theory is, that you can really find it from so different angles without, we would expect, yeah, maybe one can do that, but you find many theories and that have nothing to do. Okay, I will not present that. What I will present next Wednesday is the standard formalism, starting from the Einstein-Hilbert action, doing this decomposition, identifying P's and Q's, and deriving the constraints and discussing the constraints. And in 2 weeks, we quantize the constraints and then start to make physics with them. So, yeah, thank you for today.